All right, so in this talk, we'll be looking at surface measurements of the 2019 Ridgecrest earthquake sequence using pixel tracking of optical satellite imagery. So the first question we want to address is what controls the width and distribution of fault zone inelastic strain across a surface rupture? And the second is to understand, does the stress orientation vary between the pre, co, and post-seismic periods, or vary in space along a rupture? And so the data we'll be using are optical satellite imagery taken before and after the 2019 Ridgecrest earthquake sequence shown here. This is an event that occurred in the Eastern California shear zone and was located just north of the Garlic Fault, shown by this orange line. And so the method we're using is a fairly new image correlation technique with coseismic, which is an approach that where we can measure the full 3D surface displacement field. And the aim is to try and estimate the coseismic stress orientations using these 3D geodetic imaging data. So here's an overview of how the technique works. It's a fairly new approach, and the main idea is to have, if you have stereo images taken before an earthquake at time 1 and stereo images taken after an earthquake at time 2, you can triangulate each pixel and recover the full 3D surface displacement pattern. And the way that works in detail is essentially if you know the satellite look direction, their imaging center, and you have stereo images taken before and after the earthquake, you can then do an image correlation on the images taken before to images taken after, and then images across the earthquake. That gives you 3 correlation results with 6 independent directions of motion. From that, you can then invert for the 3D displacement patterns. That's 3 unknowns, and then also the elevation, which is 1 unknown. So you can, so then you have an overdetermined inverse problem. All right, so the data we use here are a mix of satellite images from WorldView and Spot. This is shown by the different colors here. This is the Ridgecrest rupture right here. So here we use coseismic phase correlator, and this gives a result with an image resolution of 12 meters. Okay, so this is showing the surface motion result. The left is showing the east-west motion, north-south direction, and the motion in the vertical direction. So the blue is areas of subsidence. So from these 3D surface displacement maps, we can measure the strain. Here we measure the 2D strain from 3D displacements, because to measure 3D strain, it requires having measurements of how the displacement varies as a function of depth, which we don't have. And so we don't believe that we can reliably extract the 3D strains because we lack direct measurement of that component. And so here we use the finite strain tensor, not the infinitesimal, because we're trying to resolve inelastic strain across the rupture, which involves fairly large strain. So the main difference between that and the infinitesimal strain is that it involves these higher order terms here. And then lastly, we estimate the dilatation, and that gives an idea where areas are expanding or contracting. And so we're going to zoom in here to the north, this northern area. And this shows, here you can see this is the horizontal motion shown by these vectors. So you can see it's kind of right lateral shear in this region, and areas where the vectors are diverging away from each other. And then here on this side, you can see there's subsidence on this side of the rupture. And so this is a part of the fault that's undergoing mostly right lateral shear. If you extend this image, the fault trace extends in a pretty linear manner in this direction, but the fault takes a right bend right here. And so you can see in the displacement maps, you have extension and then vertical subsidence. And so if we calculate the dilatational component, you can see this basically visualizes this kind of strain where we have purple positive values or areas where you have dilatation or extension. And then here on this linear segment of the rupture, you have variation from contraction to dilatation. So you have the kind of variation of dilatation along the segment because you have this variation in the releasing and restraining bands, which is what you expect if this part of the segment is mostly undergoing shear. You have this subtle curvature in the fault orientation, produces these variations in dilatation. And so you can see this again here in another transtensional right bend. You have this right lateral shear and then this component of extension, and this vertical subsidence, and there's positive dilatational extensional strain occurring in this right bend. Okay, so from these displacement maps, what we want to do is try and measure the 3D slip vector, because then we can use those to estimate the 3D stress orientations. So this is showing a profile across the rupture. The green shows the fault parallel motion. The red shows the fault perpendicular components, so perpendicular to this direction, and then the vertical component, which is measured from this displacement map. From those different components, we measure the amplitude, the total offset from those components. And so what we're doing is measuring the fault parallel, perpendicular, and the vertical components. You can then measure the full 3D slip vector. And so this is the result we get here. This is the different components, and this is the slip magnitude of just over 3 meters. And because we assume that the slip vector occurs along the fault plane, we can then estimate the slip rake and also the fault dip. So it's about 54 degrees and 108 degrees rake. Well, minus 108 degrees rake, which is an oblique normal strike slip, which is consistent with what we see here. Okay, and so from the 3D slip vectors, we've measured the fault parallel, the perpendicular, and the vertical component along the rupture. Although not along across the entire rupture, we're still working to process more images and acquire more measurements, but we have measurements for most of the rupture. So this is showing the statistics for this. I'll move on quickly. And then here is the fault geometry. Probably is the fault geometry that we measure. This is showing the rake and the dip in different places. So you can see here we have left lateral slip with a rake of 0. Most of the ruptures it shows a rake of around 180 or minus 180, which is right lateral. And then we have these blue areas, which is almost 90 degrees, which is showing almost normal slip here. And so the problem is that when you have regions where the fault rake is almost right lateral or left lateral, you don't have any vertical component of motion to measure or fault perpendicular component to measure. And so it essentially becomes very difficult to measure the dip because essentially your slip rake vector becomes parallel with the fault strike, and so you only have one vector to measure 2D plane, and so it's not possible to measure the fault dip. So we had to remove most of our measurements. Around 70% of our measurements we had to remove. So showing the blue is the range of fault dips that we originally had, and then the red is what was remaining. But this still provides a diverse range of rakes and dips that we can use. And so what we want to do now is, now we have the 3D slip vectors measured, the idea is to estimate the 3D stress orientation. And so you can do that here under this key assumption that the shear stress is parallel to the slip vector. And so this follows something called the Wallace-Back criterion. This is a fairly standard approach that's used when inverting focal mechanisms or second size to measure the stress orientation. And so this is showing the forward problem here, where the A matrices contain your cosine directions. Sigma is your 3D stress tensor, and then this is your data vector, which contains our 3D slip vectors. So we can then invert that to estimate. We can invert this to estimate the 3D stress tensor shown here. And if we do an eigenvalue decomposition of this stress tensor, we can estimate the principal stresses. And lastly, we can estimate the R ratio, which gives you an idea of the relative sizes of the different stresses. And we use that. That's a useful property because we can't estimate the stress magnitude. We only get the stress orientation. So this gives you an idea of the relative size of these different principal stresses. And so here's our stress results. This is showing the trend and plunge of the sigma 1, 2, 3, the principal stresses. So the red shows an orientation about 15 degrees east and north. Sigma 2 is close to vertical, and sigma 3 is close to horizontal. And here this shows the R ratio, which this is the R shape ratio value, and this ranges from about 0.1 to 0.2. And so this is consistent with a mixed stress regime that is close to transtensional, which is consistent with what we saw along the rupture. We have these regions of normal oblique faulting. Okay, and so we can also include a constraint in the inversion if we want to, where one of the principal stresses is vertical, because we're at the surface, so that should be expected. But it's encouraging that our data our inversion pulls out a result that's pretty close to vertical. And so with this constraint, the orientation of sigma 1 and 3 don't change significantly. They're still around, still trending around 15 degrees east of north. Okay, so one of the questions you want to address is, can a single stress regime explain all of the observed surface displacements on the rupture? So on the left shows our observed slip vectors in black, and then the green are observations, the predictions from our best fitting stress model. So it's expected slip vectors from our stress model. And on the right, it shows our residuals here on the rupture. So you can see we're missing obviously a lot of measurements from the majority of the rupture, but we'll zoom into this area in the northwest. You can see our stress model does a pretty good job of explaining most of the of the variations of the slip orientation, with the residuals on the right. This shows the model fit again for the east, north, and vertical component. Overall, we find a pretty good, the model can explain most of the variance of the observations with a 87% variance reduction. For the vertical, we do a much poorer job of explaining the variance. You can see here is a pretty poor fit. And I think this is likely due to the vertical displacement maps just being noisier. But with the horizontal, we can do a pretty good job explaining the horizontal component of motion. And so really, I think we can't really come to a reliable conclusion of whether a single stress regime can explain all the surface displacements, or does it require a heterogeneous stress regime, really because we were lacking measurements along other parts of the rupture. And so we are working towards trying to recover more measurements along different parts of the surface rupture by coming up with a different way of estimating the fault dip. There are different approaches to doing that, not just with the fault slip vector. And so I think at the moment this is still kind of an open question, something we question. Okay, and so the other question was, how does the coseismic stress orientation compare to the background and post-seismic stresses? So this is showing our stress result again. Here's the result from Harderback 2020, where they were in this study. This is showing a result where the stress field was estimated from inverting background focal mechanisms. So you can see a variation of the angle east of north, this angle east of north, from along the rupture varies from about 5 to 15 degrees. And Hawkes and Jones did a similar analysis using both the background seismicity and the aftershocks, and they came up with stress orientations both from the background and the aftershocks. So this is showing the stress directions from the aftershocks. You see it's pretty consistent with what we find here. The red is sigma 1 and the blue is still sigma 2, just the colors have switched. And so we can see here that the stress orientations, just showing the trend, the plunge, and then the values in the different studies agree pretty well. So this suggests that we don't see significant rotation between the background, the coseismic, and the post-seismic stress orientations. It's possible there's a few degrees variation, but we wouldn't be able to resolve that with our analysis. And so from knowing the stress orientation and the fault orientations, we can estimate the frictional coefficient, which we find is 0.8, which is quite high, but is fairly consistent with what Hawkes and Jones found, which is 0.75, which suggests a fairly strong fault. Okay, and so the last question we want to address was, do faults that are non-optimally oriented within the stress field have wider zones of inelastic strain? So here we're looking at that right transtensional bend that we saw near the start. We're just looking at it on its side. This is a dilatational component, and you can see this is the linear segment that experienced mostly shear, and you can see the variations from the sign of the dilatation, where you can see a narrower fault zone, and then within this right transtensional bend, you can see a clear widening of the zone of strain. And so what we did is measure the fault width from these strain maps. We actually used the second invariant of the strain tensor. And then to characterize how well these two fault segments are oriented within the stress field, we use something called the fault instability. This is used in focal mechanisms to determine which nodal plane is more favorably oriented within the stress field. So higher values with this fault instability indicate faults that are more optimally oriented given the stress and the frictional coefficient. So here are our measurements. This shows the width of the fault zone on that linear segment, which varies from about 20 to 30 meters, and then within the transtensional bend it increases to upwards of around 100 meters. And this is the fault instability values that we measured from this value here. And so we can regress these two. You can see a clear dependency where as the fault becomes less and less well oriented, the fault zone width widens. And so we're showing a range of frictional coefficients just to give an idea of the sensitivity of the scaling in relation to the frictional coefficient. So this was the value that we estimated from inversion, but you can see the scaling relation doesn't really vary depending on the frictional coefficient that's chosen. Okay, so to conclude, from the 3D displacement maps, we measured the 3D slip vector, which we then used to invert for the 3D stress tensor, where we find the maximum compressive stress is about 15 degrees east of north, and we don't find significant evidence for changes in the orientation of the stress tensor with time, indicating we see large rotations with time. And we find that faults that are poorly oriented have wider zones of inelastic strain, and we think this could be an important parameter to consider and include in PFHA models, because we need to understand what controls the rupture width, because this poses a hazard to nearby infrastructure.